My name is Lucas Norder, and I'm a PhD student under Richard Norton, and I'm mainly focusing in actually optomechanical structures, where we try to develop things like these sort of light sails. In this presentation, I would refer to light sails to the laser-propelled sails, so in case that's anything you wonder. So I actually wanted to start with looking at the man-made object now furthest into space, and we all know that's Voyager 1, and just relatively recently it escaped our solar system, and this is why it's been traveling for more than 50 years, right? But if this would go until Alpha Centauri, it would take over thousands of years to actually reach it. But just imagine there's a technology we can do this in almost 20 years, and especially that's the technology, that's the dream that Starshot Breakthrough Initiative actually built onto. And what they envision is having this ultralight light sail in space. You take this huge Earth-based laser, you illuminate it, and you're able to accelerate it up to 20% of the speed of light. And then there is a question that always comes into mind, is like, what would it take to make actually a technology like this? And you can think about it, it needs to be lightweight, it probably needs to be highly reflective, and it probably needs to be affordable as well. So in the next 10 minutes, I'm going to give a talk about how we think we can actually make this technology reality, and that light sails with the smallest of structures can probably make a project as big as the Breakthrough Starshot a reality. And I want to start with the question, how would a light sail like this look like? And I think it's always good to then look at the material properties or the requirements that we have in a project like this. And one of them is we need to be sure that if we illuminate this light sail, it doesn't instantly evaporate. So we need to have a material which has a really low optical absorption. And with that, traditional metallic reflectors are actually out of the picture. Another thing we can look at is high reflectivity. So we want to have this momentum transferred to this light sail. And a material property related to this is a high refractive index. So with these two material properties, we actually can look at semiconductors. And that brings us to a new type of reflector, which are called photonic crystal mirrors. Photonic crystal mirrors are materials which have a periodic structures of materials with a different refractive index. And a really basic example of this is multi-layered structures. So we have like stacks of different materials, a laser would come in, and if you look in a little bit more detail, you see that in each layer it gets reflected. But these things are actually relatively thick, 6 microns, and we cannot really reduce any weight because we need full layers. These are way too heavy for light sail application. But then we can go a little bit thinner. We have bilayer structures. We have a substrate, and if you would look on the top, you would have like holes in the photonic crystal on top of it. And here it works a little bit different. You have the laser light coming in, the light couples into the membrane, and you have a mode, and you deconstructive interference at the bottom, constructive interference at the top, and that's why we can make highly reflective structures like this. And these are still relatively thick, 800 nanometers, and we can still not really reduce the mass. So the only option we actually go to is to make one layer, so a single layer of photonic crystals. And here, it's the same principle, but here we can reduce it to 200 nanometers, or maybe even 100 nanometers, and we can reduce the weight drastically because we have all these holes there. But it's actually good to know that these features have, these structures have nanometer-sized features. So we're talking about nanotechnology. We're talking about nanofabrication. And it's good to know that light sails are actually a completely different type of nano structures that we're used to. So if you look at the Starshot Breakthrough Initiative, you have the satellite we want to look at, and we have the light sail. And if you just look at the satellite, we're looking actually at the devices. So if we want to miniaturize these devices, we do the same thing we've done for decades. We make them smaller, we miniaturize them in X, Y, and Z. And as long as we can decrease increase the density of our devices on our satellite, we actually reduce the cost. But for our light sails, it's different. So we actually make the fabric. So if we want to make these things larger, we have to still decrease them in Z. We need to make them way larger in X and Y. So, and we do this all for only a single device. So it actually gets increasingly more expensive for structures like this. So what if we look at the actual fabrication cost? If we would make this nanostructures, we have to go into a clean room. And the highest cost for this is usually the cost you actually spend per hour in these clean rooms, and it's around 200 euros an hour. And in most literature, or what people show, is that there are structures which have so small features, we need to make them with E-beam lithography. And for this, you have an electron beam, and you have to illuminate each little detail of your design with an electron. And this is really slow, but we have really good resolution. But if you want to go faster and actually get high areas, we need to go to optical lithography. Here we have a light and we have a mask and we illuminate our photoresist. We can make large structures. Downside is we need to have larger features. But what would it mean to actually make a light sail? If you go to the initial start shot parameters, we could assume that it's a 10 square meter light sail. And what if we make it with e-beam lithography? The designs that we now see in literature, it would take over 15 years of patterning and over 26 million to make only one sail. If we use e-beam, we can already reduce it to 1 day and 3,000 euros to fabricate one sail. And this gets even more crazy if you think about that the idea is not only to do one sail, but hundreds of sails. And this is not only the only cost we think is important, but also if you look at the laser itself, is if we again take the standard Starshot parameters, where we have like a 10 gigawatt meter, these are all primarily assumptions, take 10 square meters and we take the average cost of energy of Europe last year, which is around this price, it's around 300,000 euro a minute for a launch. And this took us actually to the following question, is how can we design and manufacture LightSail to meet these engineering requirements and make it affordable? And for this, we wanted to use a different type of design method. So traditionally, you would take your photonic crystal, you put it into your physics model, and you get your performance parameter out. But what we want to do is we want to have our performance parameter, put it into an optimizer, and get a design out of it. And over, literature has shown that using inverse design methods actually gives you designs which are out of the box and outperforming traditional designs. So we started to build our neural topology optimization. And we started with a design space. We discretized this design space, and then you have parts which are material and parts which are void. We put our laser input in. We model our reflectivity. And we have a few optimization variables that we change. So we change the dielectric constant of each of these pixels, so either vacuum or material. We change the period, and we change the thickness. And now it's important to actually go and look at which parameters we care about. So we really wanted to make this a reality, so we were focusing on optical lithography. So we implemented a minimum feature size constraint by implementing an area fraction constraint. Not only that, we did not only optimize for one plane wave coming in, but two plane waves. Because if you optimize for only one plane wave, you get string-like designs, which are almost impossible to fabricate. And you get a design now which is actually more robust for alignment with the laser in the end. So we haven't talked about the actual objective yet. This is really important. Then in literature, you now most see is acceleration distance. So people start to optimize their light sails for acceleration distance. And that's the distance it takes to accelerate from zero velocity to end velocity. And it's really good to know that the light that the light sail sees actually experiences a Doppler shift. So if we look at this acceleration distance, it's a function of the reflectivity over a broader spectrum. But we just talked about these huge costs of actually putting them into space anyway, like accelerating them. So we thought it's probably also good to look at acceleration time. So the time it takes to go from zero velocity to the end velocity. And again, this acceleration time is a function of the reflectivity over a broader spectrum. So we did our first initial results. And here we found some designs that we saw before. So we saw photonic crystals having square lattices, having hexagonal lattices. But we also found a lattice which we found was extremely interesting and we didn't see before in optics or optomechatronics, which is a pentagonal lattice. So this is like a structure consisting of 4 pentagons forming a hexagon. And we're really excited to see what kind of properties it would actually bring to light sail or optics in general. So these are not optimized with a minimal feature size constraint yet. So these are way too small features. And then we optimized for acceleration distance with a minimum feature size constraint. And what we see here is that we found 2 designs which were the best. This is this hexagonal design, which is more traditional one, and this pentagonal design. And here you can see the reflectivity spectrum of this hexagonal design, which is one specific peak. And this is the one of the pentagonal, where you already see that we have multiple peaks coming up because of the different holes that we have. And acceleration distance here is 47, and for the pentagonal is 52. So you could think like, oh, hexagonal is performing way better. Traditional designs are actually good. But then we have to still look at this acceleration time, what we thought was interesting. And here you can see the trajectory it would take, so the acceleration over time of this hexagonal. You actually see that the pentagonal performs better. And with that, you can already see it's a 5-minute difference. So per launch, this pentagonal design would give you 1.5 million cost of production. But this is only optimized for acceleration distance, so we also want to optimize for acceleration time. And here I want to go a little bit more detail what actually happens in the optimizer. But you see that if you optimize for only one peak in this hexagonal example, you have one peak, you have low acceleration, and that's because we have low reflectivity at the start. And that results in a low acceleration in the beginning. And if you then optimize for acceleration time, we see that the peak shifts to the right, and we have high reflectivity in the beginning, which translates to high acceleration. Which you see if you totally ignore acceleration, if you only go for acceleration distance, you actually ignore a big part of your costs in this. We also found a good pentagonal design, but here the difference is not that big for the designs that we saw, which were optimized for acceleration distance. And this because we think we're in a design basin here, so from an optimization standpoint, these designs are actually quite close. And the same is for this hexagonal and the pentagonal design. But what makes a pentagonal design so interesting? It's because it actually gives us an extra design freedom. So here you can see that we not only have one hole we can do, which you have with hexagonal designs, but we have multiple holes, and in this case, 2 holes which are the same. And that translates to 2 peaks in our reflectivity spectrum. And this is a property which is not only interesting maybe for LightSails, but also for other optics fields. And if you have an hexagonal example, you can only have one peak because you have one hole and you practically can only shift it around. And not only that, we also found that these structures have higher area fraction, so there's more material there, which could be beneficial the moment we start to include mechanics and we start to include cooling, because we have higher area fractions. So in these optimizations, these ones are not included yet, but we think the moment we start to include these things, we're actually going to see that this could be a more beneficial photonic crystal design for these structures. So we decided to, because of all these interesting properties, to make these structures. Everybody that did anything with nanostructures knows that you go into the clean room and it's not that easy. These are really large structures with billions and billions of small holes. In the moment there's something wrong with either your cleaning, your lithography, or your etching, these things start to explode. And that's what you see here. But it wasn't for nothing, because after a few months of development, we were able to fabricate this. And what you see here is the largest suspended photonic crystal in the world at the moment. And you could maybe even say the largest light sail in the world. And if you then look at this small square in there, you have this little membrane. And this is the progress we made since the announcement of Starshot. So people were making these small membranes, and we're now already able to scale it up to these lengths. And if you now zoom in, and even zoom closer, this is where you actually see our structure that we designed. But what does this actually mean? We have to give it a little bit more perspective. And that's where it gets, I think, really interesting, that if we take this membrane and we scale it up to cover the whole center of Luxembourg, it's still only the thickness of a euro coin. And this is amazing to me. Not only that, we have to make these things, we also have to measure them. So what we did afterwards is we put them in our measurement setup, and we try to measure the reflectivity. And in the end, you can see that we have quite a good agreement with the models that we make and the reflectivity spectrum that we measured. So now I want to conclude. What did I talk about? So I talked about that LightSails follow a different economics than any other nanostructures that we've seen before, because we need to make them larger in X and Y, and this makes it more expensive to fabricate. We also showed that it's really important, if we talk about LightSails, to actually take into account mission constraints and costs, because otherwise we're not talking about the real deal and these things are not possible. Then we saw that by using inverse design, we can actually get new structures, which are not only interesting for probably LightSails, but also for optics in general. And we saw that by doing this, we were able to fabricate the highest aspect ratio LightSail, which is out there at the moment. Of course, I did not do this alone. This is the team that helped us. Special thanks to ERC and Limited Space Institutes for supporting us. And Atta Keshkekler is going to give a talk later about the dynamics of these large-scale LightSails. And Richard will give a talk more about the global scale of the projects. So I want to thank everybody for their attention, and I'm open for answering any questions.